Okay, so this is a regular pentagon. And what we're going to do with this regular pentagon is show that there are some really significant relationships that are easy to define inside the regular pentagon. And they turn out to be root 5 minus 1 over 2, which should remind you of the golden ratio if you've dealt with the golden ratio before. Okay, so the first thing I want to do on this page is look at the angle measures. And the first angle measure is to see that this angle is 108. We know in a pentagon, a regular pentagon, one measure is 108. Well, everything about this is going to be about these isosceles triangles. And this is an isosceles triangle, this big one, which means that this angle is 36 and this angle is 36. Because if you look at this big triangle, EDC, you get 36, 36, 108, which is an isosceles triangle. And that actually, same argument can be made throughout the entire pentagon, and you realize that all these angles are 36. And not only are those angles 36, but all these angles are also 36, because that's what it takes to add up to 108. So we start off with all these 36-degree angles. For the same reason, we get that this angle is 108, and this angle's 108, and this angle's 108, and this angle's 108. And we notice, wait a second, that looks like the original triangle. And we could use that. We're not going to use that one, but we totally could use that as a part of what we're going to be talking about and proving today on this video. And then further along, if we take a look at these triangles here, well, they are also, because we showed that all these segments are the same because they're all isosceles triangles and all the same isosceles triangles. So the inside ones are also isosceles triangles, and if you do 180 minus 36, you get 144 divided by 2 is 72. So all of these have 72 degrees in them. And now we're ready to acknowledge all of the two basic types of equilateral triangle or isosceles triangles we have. One is this 36, 36, 108 triangle, and then the other is this 36, 72, 72. And the 36, 72, 72 is the one we're going to use. And I want you to recognize that this is one of those, and so is this. And the fact that those two triangles are similar to each other is going to be a key part of our result. The other thing to recognize is that inside here, these 5 segments make up their own regular pentagon and are all congruent to each other. Okay, so let's take a little bit cleaner look at this. And we, as we talked about, said that these are all the same. And so we're going to call all of those X. And then we know this is Y, but we showed in that last screen that this angle is the same as that angle, making EDF an isosceles triangle, which means that D to F is also Y. And so if we want to define GF, we can define GF as Y minus X. We could also define GH as Y minus X, whichever one you wanted to consider for the same reason. And so we have this 3 different measurements, Y, X, and Y minus X. Well, if you think about these 72 or 36, 72, 72 isosceles triangles, well, one of them is this one. That's the big one here. And the other one's the small one, this one right here. And it says this is X and this is Y minus X. Because these are similar, we can do a really nice proportion. Y over X equals X over Y minus X. And so Y squared minus XY equals X squared. Now, we could go ahead and stay using this, X and Y, and we could solve it that way, but it's actually a lot easier to recognize I'm looking for the ratio of DG to DE, so X to Y as it currently is. Well, it'd be really nice if G was 1, DE was 1, the denominator was 1, so let's just let the Y equal 1, and we'll use that to create our ratio. So if Y is 1, we get Y minus X equals X squared, which, when simplified, becomes X squared plus X minus 1 equals 0 as an equation. So we apply the quadratic formula, and we get negative b, which is 1, plus or minus 1 minus 4 times 1 times negative 1, all over 2. Notice that since it's a negative 1 there and our denominator is positive, the square root better be bigger than 1 and also positive. If not, you get a negative result, and x can't be negative. X has to be positive. It's a length. So that means when we calculate this as 5, we're going to have to do plus the square root of 5, and then all over 2. So we get negative 1 plus root 5 all over 2 is our x value, which then actually is the relationship between dg and de. So we have this nice relationship between those. Notice that allows us also to find out what gh is, because gh is y minus x. So in this example, gh would equal 1 minus the x value, which was negative 1 plus root 5 over 2. And so that's like 2 over 2 minus a negative 1, so it'd give you 3 minus root 5 over 2. And so we can find GH as well, which is also the side length of that inscribed triangle. And the last thing that you can recognize is that this angle is 36, and this angle is 36. And so when you draw in that diagonal inside the smaller pentagon, it's actually the same length as AF as well. And so that turns out to just be X by itself. So all of this combined allows us to find really nice ratios inside this pentagon, and allows us to solve all kinds of problems involving a regular pentagon that we may have thought we needed to use trigonometry for, but instead actually have this exact value that kind of all centers around this negative 1 plus root 5 all over 2.